Jai Hind. Next topic is the bipolar junction transistor in common emitter configuration, and this topic has been taken from the subject Fundamentals of Electronics Engineering, subject code BEC 101, and this subject is currently running in the first year syllabus of AKTU, and I am Neha Garg, Assistant Professor in EC Department of AKGEC. So, common emitter configuration. Till now we have studied the common base configuration. Common base means in common base is connected between the input side and the output side. While in common emitter configuration, emitter is common in between the input side and the output side. And also in common emitter configuration, base is the input terminal and collector is the output terminal. Emitter is the common terminal between the input side and the output side. And common emitter configuration is generally used as amplifier, while common base is used in the high frequency applications. So in common if we connect a PNP transistor in common emitter, so like we will take an example of PNP transistor. This is our P, N and P. So here this P is the emitter and this N is the base and this P is the collector. So we will do the emitter as a common in between the input and output. So we have to take a base as a base in the input side, and we will connect in this in the forward bias. So N will connect it with the negative side and positive side will connect it with the P type, and this collector and emitter will be kept in the reverse biased. So this will be negative and this will be positive. So this will be the connection in the common emitter configuration. Now the direction of current we can do, we will see only the emitter side, and the emitter we can see this is the P type, and the direction of current will always from P to N. That's why emitter current direction would be equal to this is in this form, arrow pointing upward. And we also know that IE is equal to IC plus IB. So this IE, it would be equal to IB and it will be equal to IC according to this equation. This is for the PNP transistor, and for NPN transistor we will connect in this way, NPN. So this is the emitter, this is the base and this is the collector. So emitter, this will be forward bias, so it will be positive and it will be negative, and this collector is always kept as a reverse bias. So this will be in this form. Okay, we can see this collector is N type and this emitter is also N type. So we have to always keep the collector at the reverse bias. So we will connect this positive point with the collector side, and here also we can see this collector is P type and emitter is P type. So we have to make this collector the reverse bias. So we will put this at a negative potential and this will at a positive potential. So this, and now here the direction of the current will be, this base is P and this emitter is N. So we will also always see the emitter for the mentioning the direction of current, and direction of current is always from P to N. So that's why here the direction of current would be IE, and that's why the direction of current of IB would be here and IC would be here according to this equation. And this is the this configuration, and another configuration of plotting with the help of symbol in this way. So this is the collector, this is the base and this is the emitter. So this is our NPN transistor. So we will put in the forward bias. So this is the forward bias and this will be reverse biased. Here also the direction of current will be, this is the emitter current, this is the base current and this is the collector current. This is another configuration for the NPN transistor, and for PNP transistor it would be, this is the PNP transistor. Arrow is always kept in the emitter side, not in the collector side. So this will be, base emitter would be in forward bias. So this is forward bias and this will be reverse bias. This is forward bias and this is reverse bias. And direction of current will be like arrow is pointing upward. So that's why direction of emitter current would be in this way. And this is IB and this is IC. So this is how we can draw the diagram for the emitter configuration. We have to keep one thing in mind, that emitter is always common in between the input side and output side. In input side, what we have taken? We have taken base and emitter junction, base and emitter junction. We have kept base and emitter forward biased. And in output side, emitter is common in between input and output. So we have kept emitter here also, and we will kept emitter here also. And base is included with the emitter, because emitter is your p type and base is your n type, or it may be your n type or it may be your p type. So we have to keep the different type of semiconductor here. So that's why emitter and base both are connected. And here emitter is kept with the collector, and collector is always reverse bias with respect to the emitter. So this is how we can make the configuration for the emitter, common emitter configuration. And here in the diagram we will see that this is the input side, VBE, and the current, input current is IB. So here if we plot the input characteristics, we will see the VBE potential and we will see the current, input current is IB at constant value of VCE. This is the VC potential. Collector and emitter, the potential between the collector and emitter is the VCE. So this is at constant VCE. And for the output side we can see this is our output. So IC is the output current, VC is the output potential difference. So here we will keep VCE and IC, and at constant value of IB. So when we plot the input characteristics in case of common emitter configuration, that characteristics will be plotted in between the VBE and IB, and while keeping the VCE potential constant. And in output characteristics of the common emitter configuration, this will be plotted in between the VCE and IC, and IB will be kept constant. So this thing we have to keep in our mind for designing the input and output characteristics. So these are the these are how we can connect the NPN transistor in common emitter configuration, and this is how we can connect the PNP transistor in common emitter configuration. Direction of current is always from P to N. That's why emitter current is in this way. Emitter current is the sum of IC plus IB. So first of all we have to plot the we have to mark the IE current, and with the help of this equation we can mark the IB current and IC current. And these are the symbols for the transistor. So this is for the PNP transistor, and this is for the NPN transistor. So sorry, this is for the PNP transistor, and this is for the NPN transistor. The direction of arrow is always from P to N. Okay, this is how we can connect the common emitter configuration. This is a base and this is the emitter. So base will be, if this is the NPN transistor, so base will be forward biased. That's why we have connected positive supply, and this N will be reverse biased. So it is a negative point here. And this collector and emitter junction we have to keep collector at the reverse biased. So that's why N is connected with the positive potential here. Now this is the common emitter characteristics for the input output characteristics for the common emitter configuration. So we have seen in the previous slides that for input the graph is plotted between the VBE and IB at constant VCE, and output characteristics is plotted between the IC and VCE at constant IB. So here also this graph is between the VBE and IB. Here it also behaves as a semiconductor diode, forward bias semiconductor diode. So this characteristics very much similar to the forward biased diode. And we can see here if we are increasing the VCE 1 volt, 10 volt, 20 volt, the amount of IB is reduced, because if we increase the VCE, the reverse bias across the collector base junction will also increase, and that's why the depletion layer width across the collector base junction will also increase, and it will reduce the width of the base region. That's why recombination current will be less and base current will be reduced. So that's why while increasing this VCE, like VCE potential is always, this is the emitter, this is collector, and this is the base region. So we have reverse bias this. If this is PNP, so we have make this negative and this make it have positive. So this VCE is in reverse bias. So that's why this VCB, this region will also be in reverse bias. So if we increase this VCE, so this VCB will also increase. Reverse bias here will also increase. That's why this depletion region here it will increase and it will reduce the width of the base region, and that's why IB will reduce. That's why this curve is shifted towards here. And here we can say this equation. So here we can, if we see that IC, we have seen that IC is equal to IC majority. IC is equal to IC majority, that is we can write it alpha IE plus ICBO. Okay, so in this case we know that in output current is our IC and input current is our IB. This is our input current and this is our output current, and in case this is in the configuration of common emitter, and in common base input current was, output current was IC and input current was IE, and this equation IC is equal to alpha IE ICBO. This is for the common base configuration current, but in common emitter configuration we have to reduce this equation in the form of output and input, and our output and input are IC and IB. So we have to replace this IE with this equation. IE is equal to IC plus IB. So we will put here IC is equal to, here we will put IC plus IB plus ICBO. So we will have a IC is equal to IB upon alpha IB upon 1 minus alpha plus ICBO upon 1 minus alpha. So here IC is the output current and IB is the input current, and in previous case we have IC is equal to alpha I plus ICBO. So here IC was the output current, IE was the input current, but this equation was used in the common base configuration, and from this equation we have obtained this equation IC is equal to alpha IB upon 1 minus alpha upon plus ICBO upon 1 minus alpha. So here this IB is input current, IC is output current. Now if we put IB is equal to 0 here, if we put IB is equal to 0 here, so IC would be equal to ICBO upon 1 minus alpha. Okay, and if we will put the value of alpha is 0.99, so we will have a 10 times of ICBO. So in this case, in common emitter configuration, if we put the value of IB is equal to 0, then IC would equal to 10 times of ICBO. That's why we cannot ignore here. So there will be a graph like this part, it denotes a 10 times of ICBO. If ICBO is 25 microampere, it will be 250 times, 250 microampere will be there. That cannot be ignored. So that's why at IB is equal to 0, we will show the some amount of IC will be flowing here. Like in the case of the common base emitter, this IC would be equal to ICBO only. So we will plot this characteristics only this part at I is equal to 0. But here we will have a IB is equal to 0. We have a some ICBO here. So this is the important point here. And also this region is the active region. This region is a cutoff region, and this region is a saturation region here. So this is the equation that I have shown earlier, that ICBO upon 1 minus 0.996. So 250 times of ICBO is here. So if ICB over 1 microampere, the resulting collector current with IB0 is equal to, would be equal to 250 microampere, that is would be equal to 0.25 milliampere. So this amount of current we cannot ignore. Okay, so that's why this characteristics curve we have plotted in this way. This was the VC, and this was the IC, and this is just like here in this way. Here IB is equal to 0. This is for the common emitter, and for common base we have seen this was VCB, and this was IC, and this was like in this way. This is at IE is equal to 0, and this is as IB is equal to 0. So this amount of current is there in the case of the common emitter configuration. Now just like in the case of the common emitter we have seen amplification, common base we have seen amplification factor as alpha, and that will be equal to IC upon IE. So similarly, in case of the common emitter configuration, the amplification factor is denoted by beta, and it is given output current as IC and input current is IB. So it is like IC upon IB is there, and this when we use the DC signal it would be equal to IC upon IB, and if we use the AC signal then it would be equal to delta IC upon delta IB, and while keeping the VC as constant. And generally the value of beta is generally taken as 100, that lying in between the 50 to 400. Now this is how we can calculate the value of beta AC and beta DC, and generally the value of beta AC and beta DC we will find that both values are same. So this is the output characteristics curve for this common emitter configuration. This is the VC and this is IC, and these are the characteristics plots that have been plotted. So here we will find beta AC. Beta AC means it would be equal to delta IC upon delta IB. So if we take this point, this would be equal to 3.2 here, and this point it will be equal to 2.2. So this difference would be equal to delta IC, because this is IC2, this is IC1, so your difference is delta IC, and delta IB would be equal to 30 microampere minus 20 microampere. So by solving this we will have the value of beta AC is equal to 100, and here beta DC is equal to, beta DC we can calculate, we can take any point here, that is equal to IC value is 2.7 and IB value is 25 microampere. At 25 microampere here we can see, so this Q point is here. So the value of beta DC is 108. So beta AC is 100 and beta DC is 108. So generally beta AC and the value of beta AC and beta DC are generally same in most of the cases. After that we have seen the amplification factor in case of the common base. It was in common base it was alpha, and in common collector common emitter it is beta. So the relationship between the beta and alpha, so we can write beta as IC upon IB and alpha as IC upon IE, and we have equation IE is equal to IC plus IB. So we can write this equation as IE is equal to IC plus IB. So we can divide this equation by IC. On both sides we can divide this equation by IC. So we will have IE upon IC, that would be equal to alpha, 1 upon alpha, this would be equal to 1, and this would be equal to beta. So by rearranging this alpha and beta, we will be having the value of alpha is equal to beta plus 1 plus beta and beta is equal to alpha upon alpha minus 1. Okay, so this is how this alpha and beta both are related with each other. And also in previous slides we have obtained the value of IC in case of transistor. So common emitter transistor. So that value was alpha upon 1 minus alpha, and this was equal to IB and plus ICBO upon 1 minus alpha. So alpha upon 1 minus alpha, this alpha upon 1 minus alpha, this equation we have derived from in last slides, in previous slides. So we can replace this alpha upon 1 minus alpha with the beta. So we can write this beta IB plus ICBO 1 minus alpha, 1 upon 1 minus alpha, or this 1 upon 1 minus alpha, 1 upon 1 minus alpha would be equal to beta plus 1. If we rearrange these equations, we will find this 1 upon 1 plus alpha would be equal to beta plus 1. So this equation we can write also beta IB plus beta plus 1 ICBO. Okay, and this equation, this part we can also write it as ICEO is equal to ICBO upon 1 minus alpha. And what is this ICO? This is the collector to emitter with base is open, and this we have also calculated when our IB was 0. Whenever IB was 0, we have calculated the amount of IC that was equal to ICBO upon 1 minus alpha. So that's why this ICO is we can write this ICBO upon 1 minus alpha is equal to ICEO, that is collector to emitter with base emitter base junction open, that is IB is equal to 0. So these are the equations, this is the equation, this is another one, this is another one, and these are the different equations that we can find in different places. So input resistance, dynamic input resistance in case of common emitter. So in common emitter, dynamic input resistance is defined as the ratio of the change in input voltage, base voltage to the corresponding change in the input current or base current. Okay, like we have input characteristics in this way in common emitter. So in common emitter we have this VB and this is IB. So in this case, if we find the dynamic resistance, this is delta VB, this is delta IB. So RI would be equal to delta VBE upon delta IB. So we will see this resistance will be less, there will be a low in common emitter configuration, the input resistance is very low, we can see from the graph also. And dynamic output resistance, we have seen the output characteristics are like in this way. So here it was the VCE and here it was the IC, and if we plot the, if we find the resistance of the here, so this part is delta IC and this part is delta VCE. So it would be delta VCE upon delta IC. This is the output resistance. So here from the graph we can see the value of delta IC is very small and delta VCE is very large. That's why output resistance will be very high. So in case of common emitter has a low input impedance and high output impedance, and generally it is preferred for the amplification purpose. Like common base emitter was not used for the amplification purpose, it can be only used for the high frequency applications. After that, current gain is there. So current gain in case of the common emitter configuration, we will denote it by the beta, and it is given by the IC is equal to beta IB. Here your beta would be IC upon IB. Here IC was your output current and IB was your input current. So current gain of the transistor in common base configuration is generally high. The value of beta is generally lies in between the lie as a 100. Generally it is 100 value. That's why the amount of the collector current is very high in case of common emitter configuration. And this is the different modes there are different modes in which we connect our transistor. Like this is the common base mode, and in this mode we can see base is common in input side and output side. So this is the emitter, this is the base, and this is the collector, and this is for the NPN transistor. And this is this N or P, this is the forward bias, that's why it is negative, and here it is positive. And this side it is for reverse bias, collector base junction is reverse bias, that's why this is positive and this is negative. So this is the common base mode configuration, in which base is kept common in between the input side and output side, and it is used for the high frequency applications. And this is the common emitter configuration that we have discussed in this lecture. In this we have emitters is common in between the input side and output side. So this is the base is your, this is NPN transistor is there. So P is connected with the positive terminal, N is connected with the negative terminal. So this is the forward bias, and this N is connected with the positive, and here it is connected with the this. So this is the reverse bias. Here output current is IC, and here input current is IE, and in this case output current is IC and input current is IB. And this is the common collector configuration that we will take in another lecture. So this is the base, this is collector, and this is the emitter. So here collector is common in between the input side and output side. So this part we can see, this is the NPN transistor, and P is connected with the positive terminal, and N is connected with the negative terminal. This is the VBC, and here we can see this is the VCE. This is the VCE part. So this common collector mode is generally preferred for the impedance matching. Like common emitter is preferred for the amplification, and common base mode is used in the high frequency application, and common collector mode is used in the impedance matching. Impedance matching means we have to match the impedance at the source side and at the load side, so as to transfer the maximum power to the load side. Like we have a speakers, a microphone is there. So microphone converts the sound signal into the electrical signal, and that electrical signal will be amplified by the amplifier, and after that amplified signal is given to the loudspeaker. So there is a requirement of the impedance matching. Like after microphone there is an amplifier, and after amplifier there is a loudspeaker. So there must be a impedance of the loudspeaker should be matched with the impedance of the amplifier. So that's why here we insert a common collector stage here, because common collector have a high input impedance and low output impedance. So it provides the impedance matching between the amplifier and the your loudspeaker, because loudspeaker generally has a low impedance in comparison to the amplifier. Amplifier has a high impedance and loudspeaker has a low impedance. So when power is transferred from amplifier to loudspeaker, it will be lost. So that's why common collector is inserted in between the amplifier and your loudspeaker, because common collector has a high input impedance and low output impedance. So high input impedance will be connected with the amplifier, and low input impedance will be connected with the loudspeaker. So this will be a this is how we can explain the impedance matching, that the common collector configuration is used in the impedance matching. And here also there is a output current would be equal to emitter current, and input current would be equal to IB, base current. And here the amplification factor is given by the alpha, here the amplification factor is given by the beta, and here the amplification factor is given by the gamma. So these are the differences between the transistor, different type of transistor, that is the common base configuration, common emitter configuration, and common collector configuration. So in common base we have observed low impedance is there, that is the 100 ohm, and in common emitter impedance is more in comparison to the input resistance, that is 750, and in common collector impedance is generally, input impedance is generally very high in case of common collector. In case and with regards to the output resistance, in common base output resistance is very high and it is about 450 kilo ohm, but in case of a common emitter it is 45 kilo ohm, and in case of common collector it is about 50 ohm, and voltage gain in this case is 150 and here 500 and here it is less than 1. So this is common collector is basically not preferred for the amplification, it is only used for the impedance matching. Okay, and that's why the application, main application is of common base is high frequency, and this is for the audio frequency applications, and this is for the impedance matching. This is preferred for the, basically preferred for the amplification. Here we have seen the amplification factor as alpha, that's have a value of 0.99, and here its value is like equal to 100. So this is all about the different type of configurations of common base, common emitter, and common collector. In next lectures we will discussing about the common collector configuration also. Thank you.